Learning objectives. In this chapter, the user would learn the following case studies in detail: the Unix system, the Linux system, Windows Server. The Linux system. This chapter presents an in-depth examination of the Linux operating system. By examining a complete real system, we can see how the concepts we have discussed relate both to one another and to practice. Linux is a variant of Unix that has gained popularity over the last several decades, powering devices as small as mobile phones and as large as room-filling supercomputers. In this chapter, we look at the history and development of Linux and cover the user and programmer interfaces that Linux presents, interfaces that owe a great deal to the Unix tradition. We also discuss the design and implementation of these interfaces. Linux is a rapidly evolving operating system. This chapter describes developments through the Linux 3.2 kernel, which was released in 2012. The Linux file system. Linux history. Linux looks and feels much like any other Unix system. Indeed, Unix compatibility has been a major design goal of the Linux project. However, Linux is much younger than most Unix systems. Its development began in 1991 when a Finnish university student, Linus Torvalds, began developing a small but self-contained kernel for the 80386 processor, the first true 32-bit processor in Intel's range of PC-compatible CPUs. Early in its development, the Linux source code was made available free both at no cost and with minimal distributional restrictions on the Internet. As a result, Linux's history has been one of collaboration by many developers from all around the world, corresponding almost exclusively over the Internet. From an initial kernel that partially implemented a small subset of the Unix system services, the Linux system has grown to include all of the functionality expected of a modern Unix system. In its early days, Linux development revolved largely around the central operating system kernel, the core, privileged executive that manages all system resources and interacts directly with the computer hardware. We need much more than this kernel, of course, to produce a full operating system. We thus need to make a distinction between the Linux kernel and a compatible Linux system. The Linux kernel is an original piece of software developed from scratch by the Linux community. The Linux system, as we know it today, includes a multitude of components, some written from scratch, others borrowed from other development projects, and still others created in collaboration with other teams. The basic Linux system is a standard environment for applications and user programming, but it does not enforce any standard means of managing the available functionality as a whole. As Linux has matured, a need has arisen for another layer of functionality on top of the Linux system. This need has been met by various Linux distributions. A Linux distribution includes all the standard components of the Linux system, plus a set of administrative tools to simplify the initial installation and subsequent upgrading of Linux, and to manage installation and removal of other packages on the system. A modern distribution also typically includes tools for management of file systems, creation and management of user accounts, administration of networks, web browsers, word processors, and so on. Design principles. In its overall design, Linux resembles other traditional non-microkernel Unix implementations. It is a multi-user, preemptively multitasking system with a full set of Unix-compatible tools. Linux's file system adheres to traditional Unix semantics, and the standard Unix networking model is fully implemented. The internal details of Linux's design have been influenced heavily by the history of this operating system's development. Although Linux runs on a wide variety of platforms, it was originally developed exclusively on PC architecture. A great deal of that early development was carried out by individual enthusiasts rather than by well-funded development or research facilities, so from the start Linux attempted to squeeze as much functionality as possible from limited resources. Today, Linux can run happily on a multiprocessor machine with many gigabytes of main memory and many terabytes of disk space, but it is still capable of operating usefully in under 16 MB of RAM. As PCs became more powerful and as memory and hard disks became cheaper, the original minimalist Linux kernels grew to implement more Unix functionality. Speed and efficiency are still important design goals, but much recent and current work on Linux has concentrated on a third major design goal, standardization. One of the prices paid for the diversity of Unix implementations currently available is that source code written for one may not necessarily compile or run correctly on another. Even when the same system calls are present on two different Unix systems, they do not necessarily behave in exactly the same way. The POSIX standards comprise a set of specifications for different aspects of operating system behavior. There are POSIX documents for common operating system functionality and for extensions such as process threads and real-time operations. Linux is designed to comply with the relevant POSIX documents, and at least two Linux distributions have achieved official POSIX certification because it gives standard interfaces to both the programmer and the user. Linux presents few surprises to anybody familiar with the Unix. We do not detail these interfaces here. The sections on the programmer interface and user interface of BSD apply equally well to Linux. By default, however, the Linux programming interface adheres to SVR4 Unix semantics rather than to BSD behavior. A separate set of libraries is available to implement BSD semantics in places where the two behaviors differ significantly. Many other standards exist in the Unix world, but full certification of Linux with respect to these standards is sometimes slowed because certification is often available only for a fee, and the expense involved in certifying an operating system's compliance with most standards is substantial. However, supporting a wide base of applications is important for any operating system, so implementation of standards is a major goal for Linux development even if the implementation is not formally certified. In addition to the basic POSIX standard, Linux currently supports the POSIX threading extensions, pthreads, and a subset of the POSIX extensions for real-time process control. Components of a Linux system. The Linux system is composed of three main bodies of code in line with most traditional Unix implementations. Kernel. The kernel is responsible for maintaining all the important abstractions of the operating system, including such things as virtual memory and processes. System libraries. The system libraries define a standard set of functions through which applications can interact with the kernel. These functions implement much of the operating system functionality that does not need the full privileges of kernel code. The most important system library is the C library known as libc. In addition to providing the standard C library, libc implements the user mode side of the Linux system call interface as well as other critical system-level interfaces. System utilities. The system utilities are programs that perform individual, specialized management tasks. Some system utilities are invoked just once to initialize and configure some aspects of the system. Others, known as daemons in Unix terminology, runs permanently, handling such tasks as responding to incoming network connections, accepting logon requests from terminals, and updating log files. Figure below illustrates the various components that make up a full Linux system. The most important distinction here is between the kernel and everything else. All the kernel code executes in the process's privileged mode with full access to all the physical resources of the computer. Linux refers to this privileged mode as kernel mode. Under Linux, no user code is built into the kernel. Any operating system support code that does not need to run in kernel mode is placed into the system libraries and runs in user mode. Unlike kernel mode, user mode has access only to a controlled subset of the system's resources. Kernel modules. The Linux kernel has the ability to load and unload arbitrary sections of kernel code on demand. These loadable kernel modules run in privileged kernel mode and as a consequence have full access to all the hardware capabilities of the machine on which they run. In theory, there is no restriction on what a kernel module is allowed to do. Among other things, a kernel module can implement a device driver, a file system, or a networking protocol. Kernel modules are convenient for several reasons. Linux's source code is free, so anybody wanting to write kernel code is able to compile a modified kernel and to reboot into that new functionality. However, recompiling, relinking, and reloading the entire kernel is a cumbersome cycle to undertake when you are developing a new driver. If you use kernel modules, you do not have to make a new kernel to test a new driver. The driver can be compiled on its own and loaded into the already running kernel. Of course, once a new driver is written, it can be distributed as a module so that other users can benefit from it without having to rebuild their kernels. This latter point has another implication because it is covered by the GPL license. The Linux kernel cannot be released with proprietary components added to it unless those new components are also released under the GPL and the source code for them is made available on demand. The kernel's module interface allows third parties to write and distribute on their own terms device drivers or file systems that could not be distributed under the GPL. Kernel modules allow a Linux system to be set up with a standard minimal kernel without any extra device drivers built in. Any device drivers that the user needs can be either loaded explicitly by the system at startup or loaded automatically by the system on demand and unloaded when not in use. For example, a mouse driver can be loaded when a USB mouse is plugged into the system and unloaded when the mouse is unplugged. The module support under Linux has 4 components. The module management system allows modules to be loaded into memory and to communicate with the rest of the kernel. The module loader and unloader, which are user mode utilities, work with the module management system to load a module into memory. The driver registration system allows modules to tell the rest of the kernel that a new driver has become available. A conflict resolution mechanism allows different device drivers to reserve hardware resources and to protect those resources from accidental use by another driver. Process management. A process is the basic context in which all user-requested activity is serviced within the operating system. To be compatible with other Unix systems, Linux must use a process model similar to those of other versions of Unix. Linux operates differently from the Unix in a few key places. However, in this section we review the traditional Unix process model and introduce Linux's threading model. The fork function and execute function process model. The basic principle of Unix process management is to separate into 2 steps 2 operations that are usually combined into one, the creation of a new process and the running of a new program. A new process is created by the fork function system call and a new program is run after a call to the execute function. These are 2 distinctly separate functions. We can create a new process with fork function without running a new program. The new subprocess simply continues to execute exactly the same program at exactly the same point that the first parent process was running. In the same way, running a new program does not require that a new process be created first. Any process may call execute function at any time. A new binary object is loaded into the process's address space, and the new executable starts executing in the context of the existing process. This model has the advantage of great simplicity. It is not necessary to specify every detail of the environment of a new program in the system call that runs that program. The new program simply runs in its existing environment. If the parent process wishes to modify the environment in which a new program is to be run, it can fork and then, still running the original executable in a child process, make any system calls it requires to modify that child process before finally executing the new program. Under Unix, then, a process encompasses all the information that the operating system must maintain to track the context of a single execution of a single program. Under Linux, we can break down this context into a number of specific sections. Broadly, process properties fall into three groups: the process identity, environment, and context. Process identity. A process identity consists mainly of the following items: process ID, PID. Each process has a unique identifier. The PID is used to specify the process to the operating system when an application makes and associate the process with a process group, typically a tree of processes forked by a single user command and login session. Credentials. Each process must have an associated user ID and one or more group IDs that determine the rights of a process to access system resources and files. Personality. Process personalities are not traditionally found on Unix systems, but under Linux, each process has an associated personality identifier that can slightly modify the semantics of certain system calls. Personalities are primarily used by emulation libraries to request that system calls be compatible with certain varieties of Unix. Namespace. Each process is associated with a specific view of the file system hierarchy called its namespace. Most processes share a common namespace and thus operate on a shared file system hierarchy. Processes and their children can, however, have different namespaces, each with a unique file system hierarchy, their own root directory, and a set of mounted file systems. Most of these identifiers are under the limited control of the process itself. This process group and session identifiers can be changed if the process wants to start a new group or session. Its credentials can be changed subject to appropriate security checks. However, the primary PID of a process is unchangeable and uniquely identifies that process until termination. Process environment. A process's environment is inherited from its parent and is composed of two null-terminated vectors, the argument vector and the environment vector. The argument vector simply lists the command line arguments used to invoke the running program. It conventionally starts with the name of the program itself. The environment vector is a list of name equals value pairs that associates named environment variables with arbitrary textual values. The environment is not held in kernel memory but is stored in the process's own user mode address space as the first datum at the top of the process's stack. The argument environment vectors are not altered when a new process is created. The new child process will inherit the environment of its parent. However, a completely new environment is set up when a new program is invoked. On calling execute function, a process must supply the environment for the new program. The kernel passes these environment variables to the next program, replacing the processor's current environment. The kernel otherwise leaves the environment and command line vectors alone, their interpretations left entirely to the user mode libraries and applications. The passing of environment variables from one process to the next and the inheriting of these variables by the children of a process provide flexible ways to pass information to components of the user mode system software. Various important environment variables have conventional meanings to related parts of the system software. For example, the TERM variable is set up to name the type of terminal connected to a user's login session. Many programs use this variable to determine how to perform operations on the user's display, such as moving the cursor and scrolling a region of text. Programs with multilingual support use the lang variable to determine the language in which to display system messages for programs that include multilingual support. The environment variable mechanism custom tailors the operating system on a per-process basis. Users can choose their own languages or select their own editors independently of one another. Process context. The process identity and environment properties are usually set up when a process is created and not changed until that process exits. A process may choose to change some aspects of its identity if it needs to do so, or it may alter its environment. In contrast, process context is the state of the running program at any one time. It changes constantly. Process context includes the following parts. Scheduling context. The most important part of the process context is its scheduling context, the information that the scheduler suspend and restart the process. This information includes saved copies of all the process's registers. Floating point registers are stored separately and are restored only when needed. Thus, processes that do not use floating point arithmetic do not incur the overhead of saving that state. The scheduling context also includes information about scheduling priority and about any outstanding signals waiting to be delivered to the process. A key part of the scheduling context is the process's kernel stack, a separate area of kernel memory reserved for use by kernel mode code. Both system calls and interrupts that occur while the process is executing will use the stack. Accounting. The kernel maintains accounting information about the resources currently being consumed by each process and the total resources consumed by the process in its entire lifetime so far. File table. The file table is an array of pointers to kernel file structures representing open files. When making file I/O system calls, processors refer to files by an integer known as a file descriptor (FD) that the kernel uses to index into this table. File system context. Whereas the file table lists the existing open files, the file system context applies to requests to open new files. The file system context includes the processor's root directory, current working directory, and namespace. Signal handler table. Unix systems can deliver asynchronous signals to a process in response to various external events. The signal handler table defines the action to take in response to a specific signal. Valid actions include ignoring the signal, terminating the process, and invoking a routine in the processor's address space. Scheduling. Scheduling is the job of allocating CPU time to different tasks within an operating system. Linux, like all Unix systems, supports preemptive multitasking. In such a system, the process scheduler decides which process runs and when. Making these decisions in a way that balances fairness and performance across many different workloads is one of the more complicated challenges in modern operating systems. Normally, we think of scheduling as the running and interrupting of user processes, but another aspect of scheduling is also important to Linux, the running of the various kernel tasks. Kernel tasks encompass both tasks that are requested by a running process and tasks that execute internally on behalf of the kernel itself, such as tasks spawned by Linux's I/O subsystem. Process scheduling. Linux has process scheduling algorithms. One is a time-sharing algorithm for fair, preemptive scheduling among multiple processes. The other is designed for real-time tasks where absolute priorities are more important than fairness. Earlier versions ran a variation of the traditional Unix scheduling algorithm. This algorithm does not provide adequate support for SMP systems, does not scale well as the number of tasks on the system grows, and does not maintain fairness among interactive tasks, particularly on systems such as desktops and mobile devices. Version 2.5 implemented a scheduling algorithm that selects which task to run in constant time, known as O1, regardless of the number of tasks or processes in the system. The new scheduler also provided increased support for SMP, including processor affinity and load balancing. These changes, while improving scalability, did not improve interactive performance or fairness, and, in fact, made these problems worse under certain workloads. Consequently, the process scheduler was overhauled a second time with Linux kernel version 2.6. This version ushered in the completely fair scheduler CFS. The Linux scheduler is a preemptive, priority-based algorithm with two separate priority ranges, a real-time range from 0 to 99 and a nice value ranging from 20 to 19. Smaller nice values indicate higher priorities. Thus, by increasing the nice value, you are decreasing your priority and being nice to the rest of the system. CFS is a significant departure from the traditional Unix process scheduler. In the latter, the core variables in the scheduling algorithm are priority and time slice. The time slice is the length of time, the slice of the processor that a process is afforded. Traditional Unix systems give processes a fixed time slice, perhaps with the boost or penalty for high or low priority processes respectively. A process may run for the length of its time slice and higher priority processes run before lower priority processes. It is a simple algorithm that many non-Unix systems employ. Such simplicity worked well for the early time-sharing systems but has proved incapable of delivering good interactive performance and fairness on today's modern desktops and mobile devices. CFS introduced a new scheduling algorithm called fair scheduling that eliminates time slices in the traditional sense. Instead of time slices, all processes are allotted a proportion of the process's time. CFS calculates how long a process should run as a function of the total number of runnable processes. Memory management. Memory management under the Linux has two components. The first deals with allocating and freeing physical memory, pages, groups of pages, and small blocks of RAM. The second handles virtual memory, which is memory mapped into the address space of running processes. In this section, we describe these two components and then examine the mechanisms by which the loadable components of a new program are brought into a process's virtual memory in response to an execute function system call. Management of physical memory. Due to specific hardware constraints, Linux separates physical memory into four different zones or regions. Zone DMA, Zone DMA32, Zone Normal, Zone High Mem. These zones are architecture specific. For example, on the Intel x86 32 architecture, Certain ISA, industry standard architecture devices can only access the lower 16 MB of physical memory using DMA. On these systems, the first 16 MB of physical memory comprise zone DMA. On other systems, certain devices can only access the first 4 GB of physical memory despite supporting 64-bit addresses. On such systems, the first 4 GB of physical memory comprise Zone DMA 32. Zone High Mem for high memory refers to physical memory that is not mapped into the kernel address space. For example, on the 32-bit Intel architecture where 232 provides a 4 GB address space, the kernel is mapped into the first 896 MB of the addressing space. The remaining memory is referred to as high memory and is allocated from Zone High Mem. Finally, Zone Normal comprises everything else, the normal, regularly mapped pages. Whether an architecture has a given zone depends on its constraints. A modern 64-bit architecture such as Intel x86-64 has a small 16 MB zone DMA for legacy devices and all the rest of its memory in zone normal with no high memory. The relationship of zones and physical addresses on the Intel x86-32 architecture is shown in figure below. The kernel maintains a list of free pages for each zone. When a request for physical memory arrives, the kernel satisfies the request using the appropriate zone. The primary physical memory manager in the Linux kernel is the page allocator. Each zone has its own allocator, which is responsible for allocating and freeing all physical pages for the zone and is capable of allocating ranges of physically contiguous pages on request. The allocator uses a buddy system to keep track of available physical pages. In this scheme, adjacent units of allocatable memory are paired together, hence its name. Each allocatable memory region has an adjacent partner or buddy. Whenever two allocated partner regions are freed up, they are combined to form a larger region, a buddy heap. That larger region also has a partner with which it can combine to form a still larger free region. Conversely, if a small memory request cannot be satisfied by allocation of an existing small free region, then a larger free region will be subdivided into two partners to satisfy the request. Separate linked lists are used to record the free memory regions of each allowable size. Under Linux, the smallest size allocatable under this mechanism is a single physical page. Figure below shows an example of buddy heap allocation. A 4 KB region is being allocated, but the smallest available region is 16 KB. The region is broken up recursively until a piece of the desired size is available. Ultimately, all memory allocations in the Linux kernel are made either statically by drivers that reserve a contiguous area of memory during system boot time or dynamically by the page allocator. However, kernel functions do not have to use the basic allocator to reserve memory. Several specialized memory management subsystems use the underlying page allocator to manage their own pools of memory. The most important are the virtual memory system, the kmalloc function variable length allocator, the slab allocator used for allocating memory for kernel data structures, and the page cache used for caching pages belonging to files. Many components of the Linux operating system need to allocate entire pages on request, but often smaller blocks of memory are required. The kernel provides an additional allocator for arbitrary sized requests, where the size of a request is not known in advance and may be only a few bytes. Analogous to the C language's malloc function, this kmalloc function serve allocates entire physical pages on demand but then splits them into smaller pieces. The kernel maintains lists of pages in use by the kmalloc function service. Allocating memory involves determining the appropriate list and either taking the first free piece available on the list or allocating a new page and splitting it up. Memory regions claimed by the kmalloc function system are allocated permanently until they are freed explicitly with the corresponding call to kfree function. The kmalloc function system cannot reallocate or reclaim these regions in response to memory shortages. Another strategy adopted by Linux for allocating kernel memory is known as slab allocation. A slab is used for allocating memory for kernel data structures and is made up of one or more physically contiguous pages. A cache consists of one or more threads, slabs. There is a single cache for each unique kernel data structure. For example, a cache for the data structure representing process descriptors, a cache for file objects, a cache for inodes, and so forth. Each cache is populated with objects that are instantiations of the kernel data structure the cache represents. For example, the cache representing inodes stores instances of inode structures, and the cache representing process descriptors stores instances of process descriptor structures. The relationship among slabs, caches, and objects is shown in figure below. The figure shows two kernels objects 3 KB in size and 3 objects 7 KB in size. These objects are stored in the respective caches for 3 KB and 7 KB objects. The slab allocation algorithm uses caches to store kernel objects. When a cache is created, a number of objects are allocated to the cache. The number of objects in the cache depends on the size of the associated slab. For example, a 12 KB slab made up of 3 contiguous 4 KB pages could store 6 2 KB objects. Initially, all the objects in the cache are marked as free. When a new object for a kernel data structure is needed, the allocator can assign any free object from the cache to satisfy the request. The object assigned from the cache is marked as used. Let's consider a scenario in which the kernel requests memory from the slab allocator for an object representing a process descriptor. In Linux systems, a process descriptor is one of the type struct task struct which requires approximately 1.7 KB of memory. When the Linux kernel creates a new task, it requests the necessary memory for the struct task struct object from its cache. The cache will fulfill the request using a struct task struct object that has already been allocated in a slab and is marked as free. In Linux, a slab may be in one of the 3 possible states. Full. All objects in the slab are marked as used. Empty. All objects in the slab are marked as free. Partial. The slab consists of both used and free objects. Virtual memory. The Linux virtual memory system is responsible for maintaining the address space accessible to each process. It creates pages of virtual memory on demand and manages loading those pages from disk and swapping them back out to disk as required. Under Linux, the Virtual Memory Manager maintains 2 separate views of a process's address space, as a set of separate regions and as a set of pages. The first view of an address space is the logical view, describing instructions that the virtual memory system has received concerning the layout of the address space. In this view, the address space consists of a set of non-overlapping regions, each region representing a contiguous, page-aligned subset of the address space. Each region is described internally by a single VM area struct structure that defines the properties of the region, including the process's read, write, and execute permissions in the region, as well as information about any files associated with the region. The regions for each address space are linked into a balanced binary tree to allow fast lookup of the region corresponding to any virtual address. File systems. Linux retains Unix's standard file system model. In Unix, a file does not have to be an object stored on disk or fetched over a network from a remote file server. Rather, Unix files can be anything capable of handling the input or output of a stream of data. Device drivers can appear as files, and inter-process communication channels or network connections also look like files to the user. The Linux kernel handles all these types of files by hiding the implementation details of any single file type behind a layer of software, the Virtual File System, VFS. Here we first cover the virtual file system and then discuss the standard Linux file system, ext3. The Virtual File System. The Linux VFS is designed around object-oriented principles. It has two components, a set of definitions that specify what file system objects are allowed to look like and a layer of software to manipulate the objects. The VFS defines four main object types. An inode object represents an individual file. A file object represents an open file. A superblock object represents an entire file system. A directory object represents an individual directory entry. For each of these four object types, the VFS defines a set of operations. Every object of one of these types contains a pointer to a function table. The function table lists the addresses of the actual functions that implement the defined operations for that object. For example, an abbreviated API for some of the file objects operations includes integer open, provided in brackets, open a file, size tread, provide in brackets, read from a file, size twrite, provide in brackets, write to a file, integer mmap, write in brackets, memory map a file. The complete definition of the file object is specified in the struct file operations, which is located in the file /usr/include/linux/fs.h. An implementation of the file object for a specific file type is required to implement each function specified in the definition of the file object. The VFS software layer can perform an operation on one of the file system objects by calling the appropriate function from the object's function table without having to know in advance exactly what kind of object it is dealing with. The VFS does not know or care whether an inode represents a networked file, a disk file, a network socket, or a directory file. The appropriate function for that file's read function operation will always be at the same place in its function table, and the VFS software layer will call that function without caring how the data are actually read. Inode. The inode and file objects are mechanisms used to access files. An inode object is a data structure containing pointers to the disk blocks that contain the actual file contents, and a file object represents a point of access to the data in an open file. A process cannot access an inode's contents without first obtaining a file object pointing to the inode. The file object keeps track of where in the file the process is currently reading or writing to keep track of sequential file I/O. It also remembers the permissions, for example read or write, requested when the file was opened and tracks the process's activity if necessary to perform adaptive read-ahead, fetching file data into memory before the process requests the data to improve performance. File objects typically belong to a single process, but inode objects do not. There is one file object for every instance of an open file, but always only a single inode object. Even when a file is no longer in use by any process, its inode object may still be cached by the VFS to improve performance if the file is used again in the near future. All cached file data are linked onto a list in the file's inode object. The inode also maintains standard information about each file, such as the owner, size, and time most recently modified. Directory files are dealt with slightly differently from other files. The Unix programming interface defines a number of operations on directories, such as creating, deleting, and renaming a file in a directory. The system calls for these directory operations do not require that the user open the files concerned, unlike the case for reading or writing data. The VFS therefore defines these directory operations in the inode object rather than in the file object. The superblock object represents a connected set of files that form a self-contained file system. The operating system kernel maintains a single superblock object for each disk device mounted as a file system and for each networked file system currently connected. The main responsibility of the superblock object is to provide access to inodes. The VFS identifies every inode by a unique file system /inode number pair, and it finds the inode corresponding to a particular inode number by asking the superblock object to return the inode with that number. Finally, a dentry object represents a directory entry which may include the name of a directory in the path name of a file, such as /usr, or the actual file, such as studio.h. For example, the file /usr/include/studio.h contains the directory entries 1/2 usr, 3 include, and 4 studio.h. Each of these values is represented by a separate dentry object. The Linux process file system. The flexibility of the Linux VFS enables us to implement a file system that does not store data persistently at all, but rather provides an interface to some other functionality. The Linux process file system, known as the /proc file system, is an example of a file system whose contents are not actually stored anywhere, but are computed on demand according to user file I/O requests. A /proc file system is not unique to Linux. SVR for Unix introduced a /proc file system as an efficient interface to the kernel's process debugging support. Each subdirectory of the file system corresponded not to a directory on any disk, but rather to an active process on the current system. A listing of the file system reveals one directory per process, with the directory name being the ASCII decimal representation of the processor's unique process identifier, PID. Linux implements such a /proc file system, but extends it greatly by adding a number of extra directories and text files under the file system's root directory. These new entries correspond to various statistics, but the kernel and the associated loaded drivers. The /proc file system provides a way for programs to access this information as plain text files. The standard Unix user environment provides powerful tools to process such files. For example, in the past, the traditional Unix ps command for listing the states of all running processes has been implemented as a privileged process that reads the process state directly from the kernel's virtual memory. Under Linux, the command is implemented as an entirely unprivileged program that simply passes and formats the information from /proc. The /proc file system must implement two things: a directory structure and the file contents within. Because a Unix file system is defined as a set of file and directory inodes identified by their inode numbers, the /proc file system must define a unique and persistent inode number for each directory and the associated files. Input and output. To the user, the I/O system in Linux looks much like that in any Unix system. That is, to the extent possible, all device drivers appear as normal files. Users can open an access channel to a device in the same way they open any other file. Devices can appear as objects within the file system. The system administrator can create special files within a file system that contain references to a specific device driver, and a user opening such a file will be able to read from and write to the device referenced. By using the normal file protection system, which determines who can access which file, the administrator can set access permissions for each device. Linux splits all devices into three classes: block devices, character devices, and network devices. Figure below illustrates the overall structure of the device driver system. Block devices include all devices that allow random access to completely independent, fixed-size blocks of data, including hard disks and floppy disks, CD-ROMs and Blu-ray disks, and flash memory. Block devices are typically used to store file systems, but direct access to a block device is also allowed so that programs can create and repair the file system that the device contains. Applications can also access these block devices directly if they wish. For example, a database application may prefer to perform its own fine-tuned layout of data onto a disk rather than using the general-purpose file system. Character devices include most other devices such as mice and keyboards. The fundamental difference between block and other character devices is random access. Block devices are accessed randomly, while character devices are accessed serially. For example, seeking a certain position in a file might be supported for a DVD but makes no sense for a pointing device such as a mouse. Network devices are dealt with differently from block and character devices. Users cannot directly transfer data to network devices. Block devices. Block devices provide the main interface to all disk devices in a system. Performance is particularly important for disks, and the block device system must provide functionality to ensure that disk access is as fast as possible. The functionality is achieved through the scheduling of I/O operations. In the context of block devices, a block represents the unit with which the kernel performs I/O. When a block is read into memory, it is stored in a buffer. The request manager is the layer of software that manages the reading and writing of buffer contents to and from a block device driver. A separate list of requests is kept for each block device driver. Traditionally, these requests have been scheduled according to a unidirectional elevator C-scan algorithm that exploits the order in which requests are inserted in and removed from the lists. The request lists are maintained in sorted order of increasing starting sector number. When a request is accepted for processing by a block device driver, it is not removed from the list. It is removed only after the I/O is complete, at which point the driver continues with the next request in the list, even if new requests have been inserted in the list before the active request. As new I/O requests are made, the request manager attempts to merge requests in the lists. Linux kernel version 2.6 introduced a new I/O scheduling algorithm. Although a simple elevator algorithm remains available, the default I/O scheduler is now the completely fair queuing CFQ scheduler. The CFQ I/O scheduler is fundamentally different from elevator-based algorithms. Instead of sorting requests into a list, CFQ maintains a set of lists, by default, one for each process. Requests originating from a process go in that process's list. For example, if two processes are issuing I/O requests, CFQ will maintain two separate lists of requests, one for each process. The lists are maintained according to the C-scan algorithm. CFQ services the lists differently as well. When a traditional C-scan algorithm is indifferent to a specific process, CFQ services each process's list round-robin. It pulls a configurable number of requests, by default 4, from each list before moving on to the next. This method results in fairness at the process level. Each process receives an equal fraction of the disk's bandwidth. The result is beneficial with interactive workloads where I/O latency is important. In practice, however, CFQ performs well with most workloads. Inter-process communication. Linux provides a rich environment for processes to communicate with each other. Communication may be just a matter of letting another process know that some event has occurred, or it may involve transferring data from one process to another. Synchronization and signals. The standard Linux mechanism for informing a process that an event has occurred is the signal. Signals can be sent from any process to any other process, with restrictions on signals sent to processes owned by another user. However, a limited number of signals are available and they cannot carry information. Only the fact that a signal has occurred is available to a process. Signals are not generated only by processes. The kernel also generates signals internally. For example, it can send a signal to a server process when data arrive on a network channel, to a parent process when a child terminates, or to a waiting process when a timer expires. Internally, the Linux kernel does not use signals to communicate with processes running in kernel mode. If a kernel mode process is expecting an event to occur, it will not use signals to receive notification of that event. Rather, communication about incoming asynchronous events within the kernel takes place through the use of scheduling states and wait queue structures. These mechanisms allow kernel mode processes to inform one another about relevant events, and they also allow events to be generated by device drivers or by the networking system. Whenever a process wants to wait for some event to complete, it places itself on a wait queue associated with that event and tells the scheduler that it is no longer eligible for execution. Once the event has completed, every process on the wait queue will be awoken. This procedure allows multiple processes to wait for a single event. For example, if several processes are trying to read a file from a disk, then they will all be awakened once the data have been read into memory successfully. Although signals have always been the main mechanism for communicating asynchronous events among processes, Linux also implements the semaphore mechanism of System V Unix. A process can wait on a semaphore as easily as it can wait for a signal, but semaphores have two advantages. Large numbers of semaphores can be shared among multiple independent processes, and operations on multiple semaphores can be performed atomically. Internally, the standard Linux wait queue mechanism synchronizes processes that are communicating with semaphores. Passing of data among processes. Linux offers several mechanisms for passing data among processes. The standard Unix pipe mechanism allows a child process to inherit a communication channel from its parent. Data written to one end of the pipe can be read at the other. Under Linux, pipes appear as just another type of inode to virtual file system software, and each pipe has a pair of wait queues to synchronize the reader and writer. Unix also defines a set of networking facilities that can send streams of data to both local and remote processes. Another process communications method, shared memory, offers an extremely fast way to communicate large or small amounts of data. Any data written by one process to a shared memory region can be read immediately by any other process that has mapped that region into its address space. The main disadvantage of shared memory is that, on its own, it offers no synchronization. A process can neither ask the operating system whether a piece of shared memory has been written to, nor suspend execution until such a write occurs. Shared memory becomes particularly powerful when used in conjunction with another interprocess communication mechanism that provides the missing synchronization. A shared memory region in Linux is a persistent object that can be created or deleted by processes. Such an object is treated as though it were a small independent address space. The Linux paging algorithms can elect to page shared memory pages out to disk just as they can page out a process's data pages. The shared memory object acts as a backing store for shared memory regions just as a file can act as a backing store for a memory-mapped memory region. When a file is mapped into a virtual address space region, then any page faults that occur cause the appropriate page of the file to be mapped into virtual memory. Similarly, shared memory mappings direct page faults to map in pages from a persistent shared memory object. Also, just as for files, shared memory objects remember their contents even if no processes are currently mapping them into virtual memory. Network structure. Networking is a key area of functionality for Linux. Not only does Linux support the standard Internet protocols used for most Unix to Unix communications, but it also implements a number of protocols native to other non-Unix operating systems. In particular, since Linux was originally implemented primarily on PCs rather than on large workstations or on server-class systems, it supports many of the protocols typically used on PC networks such as AppleTalk and IPX. Internally, networking in the Linux kernel is implemented by 3 layers of software. 1. The socket interface. 2. Protocol drivers. 3. Network device drivers. User applications perform all networking requests through the socket interface. This interface is designed to look like the 4.3 BSD socket layer so that any programs designed to make use of Berkeley sockets will run on Linux without any source code changes. The BSD socket interface is sufficiently general to represent network addresses for a wide range of networking protocols. This single interface is used in Linux to access not just those protocols implemented on standard BSD systems, but all the protocols supported by the system. The next layer of software is the protocol stack, which is similar in organization to SD's own framework. Whenever any networking data arrive at this layer, either from an application's socket or from a network device driver, the data are expected to have been tagged with an identifier specifying which network protocol they contain. Protocols can communicate with one another if they desire. For example, within the Internet protocol set, separate protocols manage routing, error reporting, and reliable retransmission of lost data. The protocol layer may rewrite packets, create new packets, split or reassemble packets into fragments, or simply discard incoming data. Ultimately, once the protocol layer has finished processing a set of packets, it passes them on either upward to the socket interface if the data are destined for a local connection, or downward to a device driver if the data need to be transmitted remotely. The protocol layer decides to which socket or device it will send the packet. All communication between the layers of the networking stack is performed by passing single skbuf socket buffer structures. Each of these structures contains a set of pointers into a single continuous area of memory, representing a buffer inside which network packets can be constructed. The valid data in a skbuf do not need to start at the beginning of the skbuf's buffer, and they do not need to run to the end. The networking code can add data to or trim data from either end of the packet as long as the result still fits into the skbuf. This capacity is especially important on modern microprocessors where improvements in CPU speed have far outstripped the performances of main memory. The skBuf architecture allows flexibility in manipulating packet headers and checksums while avoiding any unnecessary data copying. Security. Linux's security model is closely related to typical Unix security mechanisms. The security concerns can be classified into two groups. Authentication, making sure that nobody can access the system without first providing that she has entry rights. Access control, providing a mechanism for checking whether a user has the right to access a certain object and preventing access to objects as required. Authentication. Authentication in Unix has typically been performed through the use of a publicly readable password file. A user's password is combined with a random salt value and the result is encoded with a one-way transformation function and stored in the password file. The use of the one-way function means that the original password cannot be deduced from the password file except by trial and error. When a user presents a password to the system, the password is recombined with the salt value stored in the password file and passed through the same one-way transformation. If the result matches the contents of the password file, then the password is accepted. A new security mechanism has been developed by Unix vendors to address authentication problems. The Pluggable Authentication Modules (PAM) system is based on a shared library that can be used by any system component that needs to authenticate users. An implementation of this system is available under Linux. PAM allows authentication modules to be loaded on demand as specified in a system-wide configuration file. If any new authentication mechanism is added at a later date, it can be added to the configuration file and all system components will immediately be able to take advantage of it. PAM modules can specify authentication methods, account restrictions, session setup functions, and password changing functions so that when users change their passwords, all the necessary authentication mechanisms can be updated at once. Access control. Access control under Unix systems, including Linux, is performed through the use of unique numeric identifiers. A user identifier (UID) identifies a single user or a single set of access rights. A group identifier (GID) is an extra identifier that can be used to identify rights belonging to more than one user. Access control is applied to various objects in the system. Every file available in the system is protected by the standard access control mechanism. In addition, other shared objects such as shared memory sections and semaphores employ the same access system. Every object in a Unix system under user and group access control has a single UID and a single GID associated with it. User processes also have a single UID, but they may have more than one GID. If a process's UID matches the UID of an object, then the process has user rights or owner rights to that object. If the UIDs do not match but any GID of the process matches the object's GID, then group rights are conferred. Otherwise, the process has world rights to the object. Linux performs access control by assigning objects a protection mask that specifies which access modes, read, write or execute, are to be granted to processes with owner, group or world access. Thus, the owner of an object might have full read, write and execute access to a file. Other users in a certain group might be given read access but denied write access, and everybody else might be given no access at all. Summary. Linux is a modern, free operating system based on Unix standards. It has been designed to run efficiently and reliably on common PC hardware. It also runs on a variety of other platforms such as mobile phones. It provides a programming interface and user interface compatible with standard Unix systems and can run a large number of Unix applications, including an increasing number of commercially supported applications. Linux has not evolved in a vacuum. A complete Linux system includes many components that were developed independently of Linux. The core Linux operating system kernel is entirely original, but it allows much existing free Unix software to run, resulting in an entire Unix-compatible operating system free from proprietary code. The Linux kernel is implemented as a traditional monolithic kernel for performance reasons, but it is modular enough in design to allow most drivers to be dynamically loaded and unloaded at runtime. Linux is a multi-user system providing protection between processes and running multiple processes according to a time-sharing scheduler. Newly created processes can share selective parts of the execution environment with their parent processes, allowing multi-threaded programming. Inter-process communication is supported by both System V mechanisms, message queues, semaphores, and shared memory, and BSD's socket interface. Multiple networking protocols can be accessed simultaneously through the socket interface. The memory management system uses page sharing and copy on write to minimize the duplication of data shared by different processes. Pages are loaded on demand when they are first referenced and are paged back out to backing store according to an LFU algorithm if physical memory needs to be reclaimed. To the user, the file system appears as a hierarchical directory tree that obeys Unix semantics. Internally, Linux uses an abstraction layer to manage multiple file systems. Device-oriented networked and virtual file systems are supported. Device-oriented file systems access disk storage through a page cache that is unified with the virtual memory system. The Unix system. In the previous chapters, we examined many operating system principles, abstractions, algorithms, and techniques in general. Now it is time to look at some concrete systems to see how these principles are applied in the real world. We will begin with Unix because it runs on a wider variety of computers than any other operating system. It is the dominant operating system on high-end workstations and servers, but it is also used on systems ranging from notebook computers to supercomputers. It was carefully designed with a clean and despite its age, is still modern and elegant. Many important design principles are illustrated by Unix. Quite a few of these have been copied by other systems. Our discussion of Unix will start with its history and evolution of the system. Then we will provide an overview of the system to give an idea of how it is used. Although graphical interfaces may be easy for beginners, they provide little flexibility and no insight into how the system works. One problem that we will encounter is that there are many versions and clones of Unix, including AIX, BSD, OneBSD, HPUX, Linux, Minix, OSF1, SCO Unix, System V, Solaris, Xenix, and various others, and each of these has gone through many versions. Unix history. Multics, Multiplexed Information and Computing Service. Uniplexed Information and Computing Service. The first version of Unix was developed in 1969 by Ken Thompson of the research group at Bell Laboratories to use an otherwise idle PDP-7. Thompson was soon joined by Dennis Ritchie, and they, with other members of the research group, produced the early versions of Unix. Ritchie had previously worked on the Multics project, and Multics had a strong influence on the newer operating system. Even the name Unix is a pun on Multics. The basic organization of the file system, the idea of the command interpreter or the shell as a user process, the use of a separate process for each command, the original line editing characters, # to erase the last character and @ to erase the entire line, and numerous other features came directly from Multics. Ideas from other operating systems such as MITS and the XDS 940 system were also used. Ritchie and Thomson worked quietly on Unix for many years. They moved it to a PDP 1120 for a second version. For a third version, they rewrote most of the operating system in the system's programming language C instead of the previously used assembly language. C was developed at Bell Laboratories to support Unix. Unix was also moved to larger PDP-11 models such as the 1145 and 1170. Multiprogramming and other enhancements were added when it was rewritten in C and moved to systems such as the 1145 that had hardware support for multiprogramming. As Unix developed, it became widely used within Bell Laboratories and gradually spread to a few universities. The first version widely available outside Bell Laboratories was version 6, released in 1976. The version number for early Unix systems corresponds to the edition number of the Unix programmer's manual that was current when the distribution was made. The code and the manual were revised independently. In 1978, version 7 was distributed. This Unix system ran on the PDP 1170 and the Interdata 832 and is the ancestor of most modern Unix systems. In particular, it was soon ported to other PDP-11 models and to the VAX computer line. The version available on the VAX was known as 32V. Research has continued since then. History of Unix versions up to 1993. Design principles. Unix was designed to be a time-sharing system. The standard user interface, the shell, is simple and can be replaced by another if desired. The file system is a multi-level tree which allows users to create their own subdirectories. Each user data file is simply a sequence of bytes. Disk files and I/O devices are treated as similarly as possible. Thus, device dependencies and peculiarities are kept in the kernel as much as possible. Even in the kernel, most of them are confined to the device drivers. Unix supports multiple processes. A process can easily create new processes. CPU scheduling is a simple priority algorithm. FreeBSD uses demand paging as a mechanism to support memory management and CPU scheduling decisions. Swapping is used if a system is suffering from excess paging because Unix was originated by Thomson and Ritchie as a system for their own convenience. It was small enough to understand. Most of the algorithms were selected for simplicity, not for speed or sophistication. The intent was to have the kernel and libraries provide a small set of facilities that was sufficiently powerful to allow a person to build a more complex system if needed. Unix clean design has resulted in many imitations and modifications. Although the designers of Unix had a significant amount of knowledge about other operating systems, Unix had no elaborate design spelled out before its implementation. This flexibility appears to have been one of the key factors in the development of the system. Some design principles were involved, however, even though they were not made explicit at the outset. The Unix system was designed by programmers for programmers. Thus, it has always been interactive, and facilities for program development have always been a high priority. Such facilities include the program make, which can be used to check which of a collection of source files for a program need to be compiled and then to do the compiling, and the source code control system, SCCS, which is used to keep successive versions of files available without having to store the entire contents of each step. The primary version control system used by Unix is the Concurrent Version System, CVS. Due to the large number of developers operating on and using the code, the operating system is written mostly in C, which was developed to support Unix, since neither Thomson nor Ritchie enjoyed programming in assembly language. Assembly language was also necessary because of the uncertainty about the machines on which Unix would be run. It has greatly simplified the problems of moving Unix from one hardware system to another. From the beginning, Unix development systems have had all the Unix sources available online, and the developers have used the systems under development as their primary systems. This pattern of development has greatly facilitated the discovery of deficiencies and their fixes, as well as of new possibilities and their implementations. It has also encouraged the plethora of Unix variants existing today, but the benefits have outweighed the disadvantages. If something is broken, it can be fixed at a local site. There is no need to wait for the next release of the system. Such fixes, as well as new facilities, may be incorporated into later distributions. The size constraints of the PDP-11 and earlier computers used for Unix have forced a certain elegance. Where other systems have elaborate algorithms for dealing with pathological conditions, Unix just does a controlled crash called panic. Instead of attempting to cure such conditions, Unix tries to prevent them. Where other systems would use brute force or macro expansion, Unix mostly has had to develop more subtle or at least simpler approaches. These early strengths of Unix produced much of its popularity, which in turn produced new demands that challenged those strengths. Unix was used for tasks such as networking, graphics, and real-time operation, which did not always fit into its original text-oriented model. Thus, changes were made to certain internal facilities and new programming interfaces were added. Supporting these new facilities and others, particularly window interfaces, required large amounts of code, radically increasing the size of the system. For instance, networking and windowing both doubled the size of the system. This pattern in turn pointed out the continued strength of Unix. Whenever a new development occurred in the industry, Unix could usually absorb it but remain Unix. Process control. A process is a program in execution. Processes are identified by their process identifier, which is an integer. A new process is created by the fork system call. The new process consists of a copy of the address space of the original process, the same program and the same variables with the same values. Both processes, the parent and the child, continue execution at the instruction after the fork with one difference. The return code for the fork is 0 for the new child process, whereas the non-zero process identifier returned to the parent. Typically, the EXECVE system call is used after a fork by one of the two processes to replace that process's virtual memory space with a new program. The EXECVE system call loads a binary file into memory, destroying the memory image of the program containing the EXECVE system call and starts its execution. A process may terminate by using the exit system call, and its parent process may wait for that event by using the wait system call. If the child process crashes, the system simulates the exit call. The wait system call provides the process ID of a terminated child so that the parent can tell which of possibly many children's terminated. A second system call, wait3, is similar to wait but also allows the parent to collect performance statistics about the child. Between the time the child exits and the time the parent completes one of the wait system calls, the child is defunct. A defunct process can do nothing but exists merely so that the parent can collect its status information. If the parent process of a defunct process exits before a child, the defunct process is inherited by the init process, which in turn waits on it and becomes a zombie process. A typical use of these facilities is shown in figure below. Programmer interface. Like most operating systems, Unix consists of two separable parts, the kernel and the system's programs. We can view the Unix operating system as being layered, as shown in figure below. Everything below the system call interface and above the physical hardware is the kernel. The kernel provides the file system, CPU scheduling, memory management, and other operating system functions through system calls. Systems programs use the kernel-supported system calls to provide useful functions such as compilation and file manipulation. System calls define the programmer interface to Unix. The set of systems programs commonly available defines the user interface. The programmer and user interface define the context that the kernel must support. Most systems programs are written in C, and the Unix Programmer's Manual presents all system calls as C functions. A system program written in C for FreeBSD on the Pentium can generally be moved to an alpha FreeBSD system and simply recompiled even though the two systems are quite different. The details of system calls are known only to the compiler. This feature is a major reason for the portability of Unix programs. System calls for Unix can be roughly grouped into three categories: file manipulation, process control, and information manipulation. The fourth category, device manipulation, but since devices in Unix are treated as special files, the same system calls support both files and devices, although there is an extra system call for setting device parameters. Unix utility programs. A few of the most common Unix utility programs required by POSIX. User interface. Both the programmer and the user of a Unix system deal mainly with the set of systems programs that have been written and are available for execution. These programs make the necessary system calls to support their function, but the system calls themselves are contained within the program and do not need to be obvious to the user. The common systems programs can be grouped into several categories. Most of them are file or directory oriented. For example, the system's programs to manipulate directories are mkdir to create a new directory, rmdir to remove a directory, cd to change the current directory to another, and pwd to print the absolute path name of the current working directory. The ls program lists the names of the files in the current directory. Any of 28 options can ask that properties of the files be displayed also. For example, the -- option asks for a long listing showing the file name, owner, protection, date and time of creation, and size. The cp program creates a new file that is a copy of an existing file. The mv program moves a file from one place to another in the directory tree. In most cases, this move simply requires a renaming of the file. If necessary, however, the file is copied to the new location and the old copy is deleted. A file is deleted by the rm program, which makes an unlink system call. To display a file on the terminal, a user can run cat. The cat program takes a list of files and concatenates them, copying the result to the standard output, commonly the terminal. On a high-speed CRT display, of course, the file may speed by too fast to be read. The more program displays the file one screen at a time, pausing until the user types a character to continue to the next screen. The head program displays just the first few lines of a file. Tail shows the last few lines. Process management. A major design problem for operating systems is the representation of processes. One substantial difference between Unix and many other systems is the ease with which multiple processes can be created and manipulated. These processes are represented in Unix by various control blocks. No system control blocks are accessible in the virtual address space of a user process. Control blocks associated with a process are stored in the kernel. The kernel uses the information in these control blocks for process control and CPU scheduling. Process control blocks. The most basic data structure associated with processes is the process structure. A process structure contains everything that the system needs to know about a process when the process is swapped out, such as its unique process identifier, scheduling information, for example, the priority of the process, and pointers to other control blocks. There is an array of process structures whose length is defined at system linking time. The process structures of ready processes are kept linked together by the scheduler in a doubly linked list, the ready queue, and there are pointers from each process structure to the process's parent, to its youngest living child, and to various other relatives of interest, such as a list of processes sharing the same program code, text. The virtual address space of a user process is divided into text, program code, data, and stack segments. The data and stack segments are always in the same address space, but they may grow separately and usually in opposite directions. Most frequently, the stack grows down as the data grow up toward it. The text segment is sometimes, as on an Intel 8086 with separate instruction and data space, in an address space different from the data and stack, and it is usually read-only. The debugger puts a text segment in a read-write mode to allow insertion of breakpoints. Every proctext, almost all, under FreeBSD, has a pointer from its process structure to a text structure. The text structure records how many processes are using the text segment, including a pointer into a list of their process structures and where the page table for the text segment can be found on disk when it is swapped. The text structure itself is always resident in main memory. An array of such structures is allocated at system link time. The text, data, and stack segments for the processes may be swapped. When the segments are swapped in, they are paged. The page tables record information on the mapping from the process's virtual memory to physical memory. The process structure contains pointers to the page table for use when the process is resident in main memory, or the address of the process on the swap device when the process is swapped. There is no special separate page table for a shared text segment. Every process sharing the text segment has entries for its pages in the process's page table. Information about the process needed only when the process is resident, that is, not swapped out, is kept in the user structure or U structure rather than in the process structure. The U structure is mapped read-only into user virtual address space, so user processes can read its contents. It is writable by the kernel. The U structure contains a copy of the process control block or PCB, which is kept here for saving the process's general registers, stack pointer, program counter, and page table base registers when the process is not running. There is space to keep system call parameters and return values. All user and group identifiers associated with the process, not just the effective user identifier kept in the process structure, are kept here. Signals, timers, and quotas have data structures here. Of more obvious relevance to the ordinary user, the current directory and the table of open files are maintained in the user structure. Every process has both a user and a system mode. Most ordinary work is done in user mode, but when a system call is made, it is performed in system mode. The system and user phases of a process never execute simultaneously. When a process is executing in system mode, a kernel stack for that process is used rather than the user stack belonging to that process. The kernel stack for the process immediately follows the user structure. The kernel stack and the user structure together compose the system data segment for the process. The kernel has its own stack for use when it is not doing work on behalf of a process, for instance, for interrupt handling. The fork system call allocates a new process structure with a new process identifier for the child process and copies the user structure. There is ordinarily no need for a new text structure as the processes share their text. The appropriate counters and lists are merely updated. A new constructed and new main memory is allocated for the data and stack segments of the child process. The copying of the user structure preserves open file descriptors, user and group identifiers, signal handling, and most similar properties of a process. Figure illustrates how the process structure is used to find the various parts of a process. The vfork system call does not copy the data and stack to the new process. Rather, the new process simply shares the page table of the old one. A new user structure and a new process structure are still created. A common use of this system call occurs when a shell executes a command and waits for its completion. The parent process uses vfork to produce the child process because the child process wishes to use an execve immediately to change its virtual address space completely. There is no need for a complete copy of the parent process. Such data structures as are necessary for manipulation pipes may be kept in registers between the vfork and the execve. Files may be closed in one process without affecting the other process, since the kernel data structures involved depend on the user structure, which is not shared. The parent is suspended when it calls vfork until the child either calls execve or terminates, so that the parent will not change memory that the child needs. When the parent process is large, vfork can produce substantial savings in system CPU time. However, it is a fairly dangerous system call since any memory change occurs in both processes until the execve occurs. An alternative is to share all pages by duplicating the page table, but to mark the entries of both page tables as copy on write. Protection bits are set to trap any attempt to write in these shared pages. If such a trap occurs, a new frame is allocated and the shared page is copied to the new frame. The page tables are adjusted to show that this page is no longer shared and therefore no longer needs to be write protected, and execution can resume. An execve system call creates no new process or user structure. Rather, the text and data of the process are replaced. Open files are preserved, although there is a way to specify that certain file descriptors are to be closed on an execve. Most signal handling properties are preserved, but arrangements to call a specific user routine on a signal are cancelled for obvious reasons. The process identifier and most other properties of the process are unchanged. CPU scheduling. CPU scheduling in Unix is designed to benefit interactive processes. Processes are given small CPU time slices by a priority algorithm that reduces to round-robin scheduling for CPU-bound jobs. Every process has a scheduling priority associated with it. Large numbers indicate lower priority. Processes doing disk I/O or other important tasks have priorities less than P0 and cannot be killed by signals. Ordinary user processes have positive priorities and thus are less likely to be run than is any system process, although user processes can set precedence over one another through the nice command. The more CPU time a process accumulates, the lower, more positive its priority becomes, and vice versa. This negative feedback in CPU scheduling makes it difficult for a single process to take all the CPU time. Process aging is employed to prevent starvation. Older Unix systems used a 1-second quantum for the round-robin scheduling. FreeBSD reschedules processes every 0.1 second and recomputes priorities every second. The round-robin scheduling is accomplished by the timeout mechanism, which tells the clock interrupt driver to call a kernel subroutine after a specified interval. The subroutine to be called in this case causes the rescheduling and then resubmits a timeout to call itself again. The priority recomputation is also timed by a subroutine that resubmits a timeout for itself. There is no preemption of one process by another in the kernel. A process may relinquish the CPU because it is waiting on I/O or because its time slice has expired. When a process chooses to relinquish the CPU, it goes to sleep on an event. The kernel primitive used for this purpose is called sleep, not to be confused with a user-level library routine of the same name. It takes an argument which is by convention the address of a kernel data structure related to an event that the process wants to occur before that process is awakened. When the event occurs, the system process that knows about it calls wakeup with the address corresponding to the event, and all processes that had done a sleep on the same address are put in the ready queue to be run. For example, a process waiting for disk I/O to complete will sleep on the address of the buffer header corresponding to the data being transferred. When the interrupt routine for the disk driver notes that the transfer is complete, it calls wakeup on the buffer header. The interrupt uses the kernel stack for whatever process happened to be running at the time, and the wakeup is done from that system process. The process that actually does run is chosen by the scheduler. Sleep takes a second argument, which is the scheduling priority to be used for this purpose. This priority argument, if less than P0, also prevents the process from being awakened prematurely by some exceptional event such as a signal. When a signal is generated, it is left pending until the system half of the affected process next runs. This event soon, since the signal normally causes the process to be awakened if the process has been waiting for some other condition. No memory is associated with events. The caller of the routine that does a sleep on an event must be prepared to deal with a premature return, including the possibility that the reason for waiting has vanished. Race conditions are involved in the event mechanism. If a process decides, because of checking a flag in memory for instance, to sleep on an event, and the event occurs before the process can execute the primitive that does the actual sleep on the event, the process sleeping may then sleep forever. We prevent the situation by raising the hardware processor priority during the critical section so that no interrupts can occur, and thus only the process desiring the event can run until it is sleeping. Hardware processor priority is used in this manner to protect critical regions throughout the kernel and is the greatest obstacle to porting Unix to multiple processor machines. However, this problem has not prevented such porting from being done repeatedly. Many processes, such as text editors, are I/O bound and usually will be scheduled mainly on the basis of waiting for I/O. Experience suggests that the Unix scheduler performs best with I/O bound jobs, as can be observed when several CPU bound jobs, such as text formaters or language interpreters, are running. However, the negative feedback property of the priority scheme provides some long-term scheduling in that it largely determines the long-term job mix. Medium-term scheduling is done by this swapping mechanism. Memory management. Much of Unix's early development was done on a PDP-11. The PDP-11 has only 8 segments in its virtual address space, and the size of each is almost 8,192 bytes. The larger machines, such as the PDP-1170, allow separate instruction and address spaces, effectively doubling the address space and number of segments, but this address space is still relatively small. In addition, the kernel was even more severely constrained due to dededication of one data segment to interrupt vectors, another to point at the per-process system data segment, and yet another for the Unibus system I/O bus registers. Further, on the similar PDP-11s, total physical memory was limited to 256 KB. The total memory resources were insufficient to justify or support complex memory management algorithms. Thus, Unix swapped entire process memory images. Berkeley introduced paging to Unix with 3BSD. VAX 4.2 BSD is a demand-paged virtual memory system. Paging eliminates external fragmentation of memory. Internal fragmentation still occurs, but it is negligible with a reasonable small page size. Because paging allows execution with only parts of each process in memory, more jobs can be kept in main memory and swapping can be kept to a minimum. Demand paging is done in a straightforward manner. When a process needs a page and the page is not there, a page fault to the kernel occurs, a frame of main memory is allocated, and the proper disk page is read into the frame. There are a few optimizations. If the page needed is still in the page table for the process, but has been marked invalid by the page replacement process, it can be marked valid and used without any I/O transfer. Pages can similarly be retrieved from the list of free frames. When most processes are started, many of their pages are pre-paged and are put on the free list for recovery by this mechanism. Arrangements can also be made for a process to have no pre-paging on startup, but that is seldom done, as it results in more page fault overhead, being closer to pure demand paging. FreeBSD implements page coloring with paging queues. The queues are arranged according to the size of the process's L1 and L2 caches, and when a new page needs to be allocated, FreeBSD tries to get one that is optimally aligned for the cache. If the page has to be fetched from disk, it must be locked in memory for the duration of the transfer. It ensures that the page will not be selected for page replacement. Once the page is fetched and mapped properly, it must remain locked if raw physical I/O is being done on it. The page replacement algorithm is more interesting. BSD uses a modification of the second chance clock algorithm. The map of all non-kernel main memory, the core map or CMAP, is swept linearly and repeatedly by a software clock hand. When the clock hand reaches a given frame, if the frame is marked as being in use by some software condition, for example, if physical I/O is in progress using it, or if the frame is already free, the frame is left untouched and the clock hand sweeps to the next frame. Otherwise, the corresponding text or process page table entry for this frame is located. If the entry is already invalid, the frame is added to the free list. Otherwise, the page table entry is made invalid but reclaimable, that is, if it has not been paged out by the next time it is wanted, it can just be made valid again. BSD Tahoe added support for systems that implement the reference bit. On such systems, one pass of the clock hand turns the reference bit off, and a second pass places those pages whose reference bits remain off onto the free list for replacement. Of course, if the page is dirty, it must first be written to disk before being added to the free list. Page outs are done in clusters to improve performance. There are checks to make sure that the number of valid data pages for a process does not fall too low and to keep the paging device from being flooded with requests. There is also a mechanism by which a process can limit the amount of main memory it uses. The LRU clock hand scheme is implemented in the page daemon, which is process 2. Remember that the swapper is process 0 and init is process 1. This process spends most of its time sleeping, but a check is done several times per second, scheduled by a timer to see if action is necessary. If it is, process 2 is awakened. Whenever the number of free frames falls below a threshold, lots free, the page daemon is awakened. Thus, if there is always a large amount of free memory, the page daemon imposes no load on the system because it never runs. File system. The Unix file system supports two main objects, files and directories. Directories are just files with a special format, so the representation of a file is the basic Unix concept. Blocks and fragments, inodes, directories, mapping a file descriptor to an inode, disk structures, implementations, layout and allocation policies. Some important directories found in most Unix systems. Input-output system. One of the purposes of an operating system is to hide the peculiarities of specific hardware devices from the user. For example, the file system presents a simple, consistent storage facility, the file, independent of the underlying disk hardware. In Unix, the peculiarities of devices are also hidden from the bulk of the kernel itself by the I/O system. The I/O system consists of a buffer caching system, general device driver code, and drivers for specific hardware devices. Only the device driver knows the peculiarities of a specific device. The major parts of the I/O system are diagrammed in figure below. There are three main kinds of I/O in FreeBSD: block devices, character devices, and the socket interface. The socket interface, together with its protocols and network interfaces. Block devices include disks and tapes. Their distinguishing characteristic is that they are directly addressable in a fixed block size, usually 512 bytes. A block device driver is required to isolate details of tracks, cylinders, and so on from the rest of the kernel. Block devices are accessible directly through appropriate device special files such as /dev, /rp0, but they are more commonly accessed indirectly through the file system. In either case, transfers are buffered through the block buffer cache, which has a profound effect on efficiency. Character devices include terminals and line printers, but also include almost everything else except network interfaces that does not use the block buffer cache. For instance, /dev /mem is an interface to physical main memory, and /dev /null is a bottomless sink for data and an endless source of end-of-file markers. Some devices, such as high-speed graphics interfaces, may have their own buffers or may always do I/O directly into the user's data space. Because they do not use the block buffer cache, they are classed as character devices. Terminals and terminal-like devices use CLIS, which are buffers smaller than those of the block buffer cache. Block devices and character devices are the two main device classes. Device accessed by one of the two arrays of entry points. One array is for block devices, the other is for character devices. A device is distinguished by a class, block, or character and a device number. The device number consists of two parts. The major device number is used to index the array for character or block devices to find entries into the appropriate device driver. The minor device number is interpreted by the device driver as, for example, a logical disk partition or a terminal line. A device driver is connected to the rest of the kernel only by the entry points recorded in the array for its class and by its use of common buffering systems. This segregation is important for portability and for system configuration. Inter-process communication. Although many tasks can be accomplished in isolated processes, many others require inter-process communication. Isolated computing systems have long served for many applications, but networking is increasingly important. Furthermore, with the increasing use of personal workstations, resource sharing is becoming more common. Inter-process communication has not traditionally been one of Unix's strong points. Sockets. The pipe is the IPC mechanism most characteristic of Unix. A pipe permits a reliable unidirectional byte stream between two processes. It is traditionally implemented as an ordinary file with a few exceptions. It has no name in the file system, being created instead by the pipe system call. Its size is fixed, and when a process attempts to write to a full pipe, the process is suspended. Once all data previously written into the pipe have been read out, writing continues at the beginning of the file. Pipes are not true circular buffers. One benefit of this small size, usually 4096 bytes, of pipes is that pipe data are seldom actually written to disk. They usually are kept in memory by the normal block buffer cache. In FreeBSD, pipes are implemented as a special case of the socket mechanism. The socket mechanism provides a general interface not only to facilitate facilities such as pipes, which are local to one machine, but also to networking facilities. Even on the same machine, a pipe can be used only by two processes related through use of the fork system call. The socket mechanism can be used by unrelated processes. A socket is an endpoint of communication. A socket in use usually has an address bound to it. The nature of the address depends on the communication domain of the socket. A characteristic property of a domain is that processes communicating in the same domain use the same address format. A single socket can communicate in only one domain. Socket types. There are several socket types which represent classes of services. Each type may or may not be implemented in any communication domain. If a type is implemented in a given domain, it may be implemented by one or more protocols which may be selected by the user. Stream sockets. These sockets provide reliable, duplex, sequenced data streams. No data are lost or duplicated in delivery, and there are no record boundaries. This type is supported in the Internet domain by TCP. In the Unix domain, pipes are implemented as a pair of communicating stream sockets. Sequenced packet sockets. These sockets provide data streams like those of stream sockets, except that record boundaries are provided. This type is used in the Xerox AFNS protocol. Datagram sockets. These sockets transfer messages of variable size in either direction. There is no guarantee that such messages will arrive in the same order they were sent, or that they will be unduplicated, or that they will arrive at all, but the original message or record size is preserved in any datagram that does arrive. This type is supported in the Internet domain by UDP. Reliably delivered message sockets. These sockets transfer messages that are guaranteed to arrive and that otherwise are like the messages transferred using datagram sockets. This type is currently unsupported. Raw sockets. These sockets allow direct access by processes to the protocols that support the other socket types. The protocol's accessible example, in the Internet domain, it is possible to reach TCP, IP beneath that, or an Ethernet protocol beneath that. This capability is useful for developing new protocols. Network support. Almost all current Unix systems support the UUCP network facilities, which are mostly used over dial-up telephone lines to support the UUCP mail network and the Usenet news network. These are, however, rudimentary networking facilities. They do not support even remote login, much less remote procedure calls or distribute file systems. These facilities are almost completely implemented as user processes and are not part of the operating system itself. The networking framework in FreeBSD is more generalized than is either the ISO model or the ARM, although it is most closely related to the ARM, as shown in figure below. There are only 4 protocol layers in the ARM. Process applications. This layer subsumes the application, presentation, and session layers of the ISO model. Such user-level programs as the File Transfer Protocol (FTP) and Telnet remote login exist at this level. Host-to-host. This layer corresponds to ISO's transport and the top part of its network layers. Both the Transmission Control Protocol (TCP) and the Internet Protocol (IP) are in this layer, with TCP on top of IP. TCP corresponds to an ISO transport protocol and IP performs the addressing functions of the ISO network layer. Network interface. This layer spans the lower part of the ISO network layer and the entire data link layer. The protocols involved here depend on the physical network type. The ARPANET uses the IMP host protocols, whereas an Ethernet uses Ethernet protocols. Network hardware. The ARM is primarily concerned with software, so there is no explicit network hardware layer. However, any actual network will have hardware corresponding to the ISO physical layer. Windows Server. The Microsoft Windows 7 operating system is a 32 and 64-bit preemptive multitasking client operating system for microprocessors, implementing the Intel IA32 and AMD 64 instruction set architectures (ISAs). Microsoft's corresponding server operating system, Windows Server 2008 R2, is based on the same code as Windows 7 but supports only the 64-bit AMD 64 and IA64 Itanium ISAs. Windows 7 is the latest in a series of Microsoft operating systems based on its NT code, which replaced the earlier systems based on Windows 95-98. In this chapter, we discuss the key goals of Windows 7, the layered architecture of the system that has made it so easy to use, the file system, the networking features, and the programming interface. History. In the mid-1980s, Microsoft and IBM cooperated to develop the OS/2 operating system, which was written in assembly language for single-processor Intel 80286 systems. In 1988, Microsoft decided to end the joint effort with IBM and develop its own New Technology or NT portable operating system to support both the OS/2 and POSIX application programming interfaces APIs. In October 1988, Dave Cutler, the architect of the DEC VAX VMS operating system, was hired and given the charter of building Microsoft's new operating system. Originally, the team planned to use the OS/2 API as NT's native environment, but during development, NT was changed to use a new 32-bit Windows API called Win32, based on the popular 16-bit API used in Windows 3.0. The first versions of NT were Windows NT 3.1 and Windows NT 3.1 Advanced Server. At that time, 16-bit Windows was at version 3.1, Windows NT version 4.0 adopted the Windows 95 user interface and incorporated Internet Web Server and web browser software. In addition, user interface routines and all graphics code were removed into the kernel to improve performance with the side effect of decreased system reliability. Although previous versions of NT had been ported to other microprocessor architectures, the Windows 2000 version, released in February 2000, supported only Intel and compatible processors due to marketplace factors. Windows 2000 incorporated significant changes. It added Active Directory and X.500 base directory service, better networking and laptop support, support for plug-and-play devices, a distributed file system, and support for more processors and more memory. In October 2001, Windows XP was released as both an update to the Windows 2000 desktop operating system and a replacement for Windows 95-98. In 2002, the Server edition of Windows XP became available, called Windows.NET Server. Windows XP updated the graphical user interface (GUI) with a visual design that took advantage of more recent hardware advances and many new ease-of-use features. Numerous features were added to automatically repair problems in applications and the operating system itself. As a result of these changes, Windows XP provided better networking and device experience, including zero configuration wireless, instant messaging, streaming media, and digital photography, video, dramatic performance improvements for both the desktop and large multiprocessors, and better reliability and security than earlier Windows operating systems. The result was Windows 7, which was released in October 2009 along with corresponding server editions of Windows. Among the significant engineering changes in the increased use of executing tracing rather than counters or profiling to analyze system behavior. Tracing runs constantly in the system, watching hundreds of scenarios execute. When one of these scenarios fails, or when it succeeds but does not perform well, the traces can be analyzed to determine the cause. Windows 7 uses a client-server architecture like MASH to implement two operating system personalities, Win32 and POSIX, with user-level processes called subsystems. At one time, Windows also supported an OS/2 subsystem, but it was removed in Windows XP due to the demise of OS/2. The subsystem architecture allows enhancements to be made to one operating system personality without affecting the application compatibility of the other. Although the POSIX subsystem continues to be available for Windows 7, the Win32 API has become very popular and the POSIX APIs are used by only a few sites. Windows 7 Windows 7 is a multi-user operating system supporting simultaneous access through distributed services or through multiple instances of the GUI via the Windows Terminal services. The server editions of Windows 7 support simultaneous terminal server sessions from Windows desktop systems. The desktop editions of Terminal Server multiplex the keyboard, mouse, and monitor between virtual terminal sessions for each logged-on user. This feature, called fast user switching, allows users to preempt each other at the console of a PC without having to log off and log on. We noted earlier that some GUI implementation moved into kernel mode in Windows NT 4.0. It started to move into user mode again with Windows Vista, which included the Desktop Window Manager DWM as a user mode process. DWM implements the desktop compositing of Windows, providing the Windows Aero interface look on top of the Windows DirectX graphics software. DirectX continues to run in the kernel, as does the code implementing Windows' previous windowing and graphics models Win32K and GDI. Windows 7 made substantial changes to the DWM, significantly reducing its memory footprint and improving its performance. Windows XP. It was the first version of Windows to ship a 64-bit version for the IA64 in 2001 and the AMD 64 in 2005. Internally, the native NT file system NTFS and many of the Win32 APIs have always used 64-bit integers where appropriate, so the major extension to 64-bit in Windows XP was supported for large virtual addresses. However, 64-bit editions of Windows also support much larger physical memories. By the time Windows 7 shipped, the AMD 64 ISA had become available on almost all CPUs from both Intel and AMD. In addition, by that time, physical memories on client systems frequently exceeded the 4 GB limit of the IA32. As a result, the 64-bit version of Windows 7 is now commonly installed on larger client systems. Because of the AMD 64 architecture supports high-fidelity IA32 compatibility at the level of individual processors, 32 and 64-bit applications can be freely mixed in a single system. In the rest of our description of Windows 7, we will not distinguish between the client editions of Windows 7 and the corresponding server editions. They are based on the same core components and run the same binary files for the kernel and most drivers. Similarly, although Microsoft ships a variety of different editions of each release to address different market price points, few of the differences between editions are reflected in the core of the system. Design principles. Microsoft's design goals for Windows included security, reliability, Windows and POSIX application compatibility, high performance, extensibility, portability, and international support. Some additional goals, energy efficiency and dynamic device support have recently been added to this list. Windows 7 security goals required more than just adherence to the design standards that had enabled Windows NT 4.0 to receive a C2 security classification from the US government. Classification signifies a moderate level of protection from defective software and malicious attacks. Classifications were defined by the Department of Defense Trusted Computer System Evaluation Criteria, also known as the Orange Book. Extensive code review and testing were combined with sophisticated automatic analysis tools to identify and investigate potential defects that might represent security vulnerabilities. Windows bases security on discretionary access controls. System objects including files, registry settings, and kernel objects are protected by access control lists, ACLs. ACLs are vulnerable to user and programmer errors as well as to the most common attacks on consumer systems in which the user is tricked into running code, often while browsing the web. Windows 7 includes a mechanism called integrity levels that acts as a rudimentary capability system for controlling access. Objects and processes are marked as having low, medium, or high integrity. Windows does not allow a process to modify an object with a higher integrity level, no matter what the setting of the ACL. Other security measures include address space layout randomization (ASLR), non-executable stacks and heaps, and encryption and digital signature facilities. ASLR thwarts many forms of attack by preventing small amounts of injected code from jumping easily to code that is already loaded in a process as part of normal operation. This safeguard makes it likely that a system under attack will fail or crash rather than let the attacking code take control. Recent chips from both Intel and AMD are based on the AMD 64 architecture, which allows memory pages to be marked so that they cannot contain executable instruction code. Windows tries to mark stacks and memory heaps so that they cannot be used to execute code, thus preventing attacks in which a program bug allows a buffer to overflow and then is tricked into executing the contents of the buffer. This technique cannot be applied to all programs because some rely on modifying data and executing it. A column labeled Data Execution Prevention in the Windows Task Manager shows which processes are marked to prevent these attacks. System components. The main layers of the HAL, the kernel, and the executive, all of which run in kernel mode, and a collection of subsystems and services that run in user mode. The user mode subsystems fall into two categories: the environmental subsystems, which emulate different operating systems, and the protection subsystems, which provide security functions. One of the chief advantages of this type of architecture is that interactions between modules are kept simple. The remainder of this section describes these layers and subsystems. Hardware abstraction layer. The HAL is the layer of software that hides hardware chipset differences from upper levels of the operating system. The HAL exports a virtual hardware interface that is used by the kernel dispatcher, the executive, and the device drivers. Only a single version of each device driver is required for each CPU architecture, no matter what support chips might be present. Device drivers map devices and access them directly, but the chipset's specific details of mapping memory, configuring I/O buses, setting up DMA, and copying with other board-specific facilities are all provided by the HAL interfaces. Kernel. The kernel layer of Windows has four main responsibilities: thread scheduling, low-level processor synchronization, interrupt and exception handling, and switching between user mode and kernel mode. The kernel is implemented in the C language, using assembly language only where absolutely necessary to interface with the lowest level of the hardware architecture. The kernel is organized according to object-oriented design principles. An object type in Windows is a system-defined data type that has a set of attributes, data values, and a set of methods, for example, functions or operations. An object is an instance of an object type. The kernel performs its job by using a set of kernel objects whose attributes store the kernel data and whose methods perform the kernel activities. Kernel dispatcher. The kernel dispatcher provides the foundation for the executive and the subsystems. Most of the dispatcher is never paged out of memory, and its execution is never preempted. Its main responsibilities are thread scheduling and context switching, implementation of synchronization primitives, timer management, software interrupts, asynchronous and deferred procedure calls, and exception dispatching. Threads and scheduling. Like many other modern operating systems, Windows uses processes and threads for executable code. Each process has one or more threads, and each thread has its own scheduling state, including actual priority, processor affinity, and CPU usage information. There are 6 thread states: ready, standby, running, waiting, transition, and terminated. Ready indicates that the thread is waiting to run. The highest priority ready thread is moved to the standby state, which means it is the next thread to run. In a multiprocessor system, each processor keeps one thread in a standby state. A thread is running when it is executing on a processor. It runs until it is preempted by a higher priority thread, until it terminates, until its allotted execution time quantum ends, or until it waits on a dispatcher object such as an event signaling I/O completion. A thread is in the waiting state when it is waiting for a dispatcher object to be signaled. A thread is in the transition state while it waits for resources necessary for execution. For example, it may be waiting for its kernel stack to be swapped in from disk. A thread enters the terminated state when it finishes execution. Implementation of synchronization primitives. Key operating system data structures are managed as objects using common facilities for location, reference counting, and security. Dispatcher objects control dispatching and synchronization in the system. Example of these objects include the following. The event object is used to record an event occurrence and to synchronize this occurrence with some action. Notification events signal all waiting threads, and synchronization events signal a single waiting thread. The mutant provides kernel mode or user mode mutual exclusion associated with the notion of ownership. The mutex, available only in kernel mode, provides deadlock-free mutual exclusion. The semaphore object acts as a counter or gate to control the number of threads that access a resource. The thread object is the entity that is scheduled by the kernel dispatcher. It is associated with a process object which encapsulates a virtual address space. The thread object is signaled when the thread exits and the process object when the process exits. The timer object is used to keep track of time and to signal timeouts when operations take too long and need to be interrupted, or when a periodic activity needs to be scheduled. Many of the dispatcher objects are accessed from user mode via an open operation that returns a handle. The user mode code polls or waits on handles to synchronize with other threads as well as with the operating system. Software interrupts. Asynchronous and deferred procedure calls. The dispatcher implements two types of software interrupts: asynchronous procedure calls, APCs, and deferred procedure calls, DPCs, mentioned earlier. An asynchronous procedure call breaks into an executing thread and calls a procedure. APCs are used to begin execution of new threads, suspend or resume existing threads, terminate threads or processes, deliver notification that an asynchronous I/O has completed, and extract the contents of the CPU registers from a running thread. APCs are queued to specific threads and allow the system to execute both system and user code within a processor's context. User mode execution of an APC cannot occur at arbitrary times, but only when the thread is waiting in the kernel and marked alertable. Exceptions and interrupts. The kernel dispatcher also provides trap handling for exceptions and interrupts generated by hardware or software. Windows defines several architecture-independent exceptions, including memory access violation, integer overflow, floating point overflow or underflow, integer divide by zero, floating point divide by zero, illegal instruction, data misalignment, privilege instruction, page read error, access violation, paging file quota exceeded, debugger breakpoint, debugger single step. The trap handlers deal with simple exceptions. Elaborate exception handling is performed by the kernel's exception dispatcher. The exception dispatcher creates an exception record containing the reason for the exception and finds an exception handler to deal with it. When an exception occurs in kernel mode, the exception dispatcher simply calls a routine to locate the exception handler. If no handler is found, a fatal system error occurs and the user is left with the infamous blue screen of death that signifies system failure. Exception handling is more complex for user mode processes because an environmental subsystem such as POSIX system sets up a debugger port and an exception port for every process it creates. If a debugger port is registered, the exception handler sends the exception to the port. If the debugger port is not found or does not handle that exception, the dispatcher attempts to find an appropriate exception handler. If no handler is found, the debugger is called again to catch the error for debugging. If no debugger is running, a message is sent to the process's exception port to give the environmental subsystem a chance to translate the exception. For example, the POSIX environment translates Windows exception messages into POSIX signals before sending them to the thread that caused the exception. Finally, if nothing else works, the kernel simply terminates the process containing the thread that caused the exception. Executive. The Windows Executive provides a set of services that all environmental subsystems use. The services are grouped as follows: Object Manager, Virtual Memory Manager, Process Manager, Advanced Local Procedure Call Facility, I/O Manager, Cache Manager, Security Reference Monitor, Plug and Play and Power Managers, Registry and Booting. Object Manager. For managing kernel mode entities, Windows uses a generic set of interfaces that are manipulated by user mode programs. Windows calls these entities objects, and the executive component that manipulates them is the Object Manager. Examples of objects are semaphores, mutexes, events, processes, and threads. All these are dispatcher objects. Threads can block in the kernel dispatcher waiting for any of these objects to be signaled. The process, thread, and virtual memory APIs use process and thread handles to identify the process or thread to be operated on. Other examples of objects include files, sections, ports, and various internal I/O objects. File objects are used to maintain the open state of files and devices. Sections are used to map files. Local communication endpoints are implemented as port objects. User mode code accesses these objects using an opaque value called a handle, which is returned by many APIs. Each process has a handle table containing entries that track the objects used by the process. The system process, which contains the kernel, has its own handle table which is protected from user code. The handle tables in Windows are represented by a tree structure which can expand from holding 1024 handles to holding over 16 million. Kernel mode code can access an object by using either a handle or a reference pointer. Virtual Memory Manager. The executive component that manages the virtual address space, physical memory allocation, and paging is the Virtual Memory VM Manager. The design of the VM Manager assumes that the underlying hardware supports virtual to physical mapping, a paging mechanism, and transparent cache coherence on multiprocessor systems, as well as allowing multiple page table entries to map to the same physical page frame. The VM Manager in Windows uses a page-based management scheme with page sizes of 4 KB and 2 MB on AMD 64 and IA32 compatible processors and 8 KB on the IA64. Pages of data allocated to a process that are not in physical memory are either stored in the paging files on disk or mapped directly to a regular file on a local or remote file system. A page can also be marked zero fill on demand, which initializes the page with zeros before it is allocated, thus erasing the previous contents. Key areas of the kernel mode region that are not identical for all processes are the self-map, hyperspace, and session space. The hardware references a processor's page table using physical page frame numbers, and the page table self-map makes the contents of the processor's page table accessible using virtual addresses. Hyperspace maps the current processor's working set information into the kernel mode address space. Session space is used to share an instance of the Win32 and other session-specific drivers among all the processes in the same terminal server TS session. Different TS sessions share different instances of these drivers, yet they are mapped at the same virtual addresses. The lower user mode region of virtual address space is specified to each process and accessible by both user and kernel mode threads. Let's look closely at the last two of these protection settings. A no-access page raises an exception if accessed. The exception can be used, for example, to check whether a faulty program iterates beyond the end of an array, or simply to detect that the program attempted to access virtual addresses that are not committed to memory. User and kernel mode stacks use no-access pages as guard pages to detect stack overflows. Another use is to look for heap buffers overruns. Both the user mode memory allocator and the special kernel allocator used by the device verifier can be configured to map each allocation onto the end of a page, followed by a no-access page to detect programming errors that access beyond the end of an allocation. The copy-on-write mechanism enables the VM manager to use physical memory more efficiently. When two processors want independent copies of data from the same section object, the VM manager places a single shared copy into virtual memory and activates the copy-on-write property for that region of memory. If one of the processors tries to modify data in a copy-on-write page, the VM manager makes a private copy of the page for the process. A page table layout is shown below. The virtual address translation in Windows uses a multi-level page table. For IA32 and AMD64 processors, each process has a page directory that contains 512 page directory entries PDEs, 8 bytes in size. Each PDE points to a PTE table that contains 512 page table entries PTEs, 8 bytes in size. Each PTE points to a 4 KB page frame in physical memory. For a variety of reasons, the hardware requires that the page directories or PTE tables at each level of a multi-level page table occupy a single page. Thus, the number of PDEs or PTEs that fit in a page determine how many virtual addresses are translated by that page. I/O Manager. The I/O Manager is responsible for managing file systems, device drivers, and network drivers. It keeps track of which device drivers, filter drivers, and file systems are loaded, and it also manages buffer for I/O requests. It works with the VM Manager to provide memory-mapped file I/O and controls the Windows Cache Manager, which handles caching for the entire I/O system. The I/O Manager is fundamentally asynchronous, providing synchronous I/O by explicitly waiting for an I/O operation to complete. The I/O Manager provides several models of asynchronous I/O completion, including setting of events, updating of a status variable in the calling process, delivery of APCs to initiating threads, and use of I/O completion ports, which allow a single thread to process I/O completions from many other threads. Device drivers are arranged in a list for each device called a driver or I/O stack. A driver is represented in the system as a driver object. Because a single driver can operate on multiple devices, the drivers are represented in the I/O stack by a device object, which contains a link to the driver object. The I/O Manager converts requests it receives into a standard form called an I/O request packet (IRP). It then forwards the IRP to the first driver in the targeted I/O stack for processing. After a driver processes the IRP, it calls the I/O Manager either to forwarding the IRP to the next driver in the stack or, if all processing is finished, to complete the operation presented by IRP. The I/O request may be completed in a context different from the one in which it was made. For example, if a driver is performing its part of an I/O operation and is forced to block for an extended time, it may queue the IRP to a worker thread to continue processing in the system context. In the original thread, the driver returns a status indicating that the I/O request is pending so that the thread can continue executing in parallel with the I/O operation. An IRP may also be processed in interrupt service routines and completed in an arbitrary process context. Because some final processing may need to take place in the context that initiated the I/O manager uses an APC to do final I/O completion processing in the process context of the originating thread. Terminal services and fast user switching. Windows supports a GUI-based console that interfaces with the user via keyboard, mouse, and display. Most systems also support audio and video. Audio input is used by Windows voice recognition software. Voice recognition makes the system more convenient and increases its accessibility for users with disabilities. Windows 7 added support for multi-touch hardware, allowing users to input data by touching the screen and making gestures with one or more fingers. Eventually, the video input capability, which is currently used for communication applications, is likely to be used for visually interpreting gestures, as Microsoft has demonstrated for its Xbox 360 Kinect product. Other future input experiences may evolve from Microsoft's Surface computer, most often installed at public venues such as hotels and conference centers. The Surface computer is a table surface with special cameras underneath. It can track the actions of multiple users at once and recognize objects that are placed on top. The PC was, of course, envisioned as a personal computer, an inherently single-user machine. Modern Windows, however, supports the sharing of a PC among multiple users. Each user that is logged on using the GUI has a session created to represent the GUI environment he will be using and to contain all the processes created to run his applications. Windows allows multiple sessions to exist at the same time on a single machine. However, Windows only supports a single console, consisting of all the monitors, keyboards, and mice connected to the PC. Only one session can be connected to the console at a time. From the login screen displayed on the console, users can create new sessions or attach to an existing session that was previously created. This allows multiple users to share a single PC without having to log off and on between users. Microsoft calls this use of sessions fast user switching. File system. The native file system in Windows is NTFS. It is used for all local volumes. However, associated USB thumb drives, flash memory on cameras, and external disks may be formatted with the 32-bit FAT file system for portability. FAT is a much older file system format that is understood by many systems besides Windows, such as the software running on cameras. A disadvantage is that the FAT file system does not restrict file access to authorized users. The only solution for securing data with FAT is to run an application to encrypt the data before storing it on the file system. In contrast, NTFS uses ACLs to control access to individual files and support implicit encryption of individual files or entire volumes using Windows BitLocker feature. NTFS implements many other features as well, including data recovery, fault tolerance, very large files and file systems, multiple data streams, Unicode names, sparse files, journaling, volume shadow copies, and file compression. NTFS internal layout. The fundamental entity in NTFS is a volume. A volume is created by the Windows Logical Disk Management utility and is based on a logical disk partition. A volume may occupy a portion of a disk or an entire disk or may span several disks. NTFS does not deal with individual sectors of a disk, but instead uses clusters as the units of disk allocation. A cluster is a number of disk sectors that is a power of 2. The cluster size is configured when an NTFS file system is formatted. The default cluster size is based on the volume size, 4 KB for volumes larger than 2 GB. Given the size of today's disks, it may make sense to use cluster sizes larger than the Windows defaults to achieve better performance, although these performance gains will come at the expense of more internal fragmentation. NTFS uses logical cluster numbers LCNs as disk addresses. It assigns them by numbering clusters from the beginning of the disk to the end. Using this scheme, the system can calculate a physical disk offset in bytes by multiplying the LCN by the cluster size. A file in NTFS is not a simple byte stream as it is in Unix, rather it is a structured object consisting of typed attributes. Each attribute of a file is an independent byte stream that can be created, deleted, read, and written. Some attribute types for all files, including the file name or names if the file has aliases, such as an MS-DOS short name, the creation time, and the security descriptor that specifies the access control list. User data are stored in data attributes. NTFS metadata. The NTFS volumes metadata are all stored in files. The first file is the MFT. The second file, which is used during recovery if the MFT is damaged, contains a copy of the first 16 entries of the MFT. The next few files are also special in purpose. They include the files described below. The log file records all metadata updates to the file system. The volume file contains the name of the volume, the version of NTFS that formatted the volume, and a bit that tells whether the volume may have been corrupted and needs to be checked for consistency using the checkdisk program. The attribute definition table indicates which attribute types are used in the volume and what operations can be performed on each of them. The root directory is the top-level directory in the file system hierarchy. The bitmap file indicates which clusters on a volume are allocated to files and which are free. The boot file contains the startup code for Windows and must be located at a particular disk address so that it can be found easily by a simple ROM bootstrap loader. The boot file also contains the physical address of the MFT. The bad cluster file keeps track of any bad areas on the volume. NTFS uses this record for error recovery. Security. The security of an NTFS volume is derived from the Windows object model. Each NTFS file references a security descriptor which specifies the owner of the file and an access control list which contains the access permissions granted or denied to each user or group listed. Early versions of NTFS used a separate security descriptor as an attribute of each file. Beginning with Windows 2000, the security descriptor's attribute points to a shared copy with a significant savings in disk and caching space. Many files have identical security descriptors. In normal operation, NTFS does not enforce permissions on traversal of directories in file path names. However, for compatibility with POSIX, these checks can be enabled. Traversal checks are inherently more expensive since modern parsing of file path names uses prefix matching rather than directory by directory parsing of path names. Prefix matching is an algorithm that looks up strings in a cache and finds the entry with the longest match. For example, an entry for /FOO/bar/dir would be a match for /FOO/bar/dir2/dir3/myfile. The prefix matching cache allows path name traversal to begin much deeper in the tree, saving many steps. Enforcing traversal checks means that the user's access must be checked at each directory level. For instance, a user might lack permission to traverse /foo/bar, so starting at the access for /foo/bar/dir would be an error. Networking. Windows supports both peer-to-peer and client-server networking. It also has facilities for network management. The networking components in Windows provides data transport, inter-process communication, file sharing across a network, and the ability to send print job printers. Network interfaces. To describe networking in Windows, we must first mention two of the internal networking interfaces, the Network Device Interface Specification (NDIS) and the Transport Driver Interface (TDI). The NDIS interface was developed in 1989 by Microsoft and 3Com to separate network adapters from transport protocols so that either could be changed without affecting the other. NDIS resides at the interface between the data link and network layers in the ISO model and enables many protocols to operate over many different network adapters. In terms of the ISO model, the TDI is the interface between the transport layer, layer 4, and the session layer, layer 5. This interface enables any session layer component to use any available transport mechanism. Similar reasoning led to the streams mechanism in Unix. The TDI supports both connection-based and connection-less transport and has functions to send any type of data. Protocols. Windows implements transport protocols as drivers. These drivers can be loaded and unloaded from the system dynamically, although in practice the system typically has to be rebooted after a change. Windows comes with several networking protocols. Next, we discuss a number of these protocols. Server Message Block. The Server Message Block (SMB) protocol was first introduced in MS-DOS 3.1. The system uses the protocol to send I/O requests over the network. The SMB protocol has 4 message types. Session control messages are commands that start and end a redirector connection to a shared resource at the server. A redirector uses file messages to access file at the server. Printer messages are used to send data to a remote print queue and to receive status information from the queue, and messages are used to communicate with another workstation. A version of the SMB protocol was published as the Common Internet File System (CIFS) and is supported on a number of operating systems. Transmission Control Protocol, Internet Protocol. The Transmission Control Protocol, Internet Protocol, TCP/IP, suite that is used on the Internet has become the de facto standard networking infrastructure. Windows uses TCP/IP to connect to a wide variety of operating systems and hardware platforms. The Windows TCP/IP package includes the Simple Network Management Protocol, SNM, the Dynamic Host Configuration Protocol, DHCP, and the older Windows Internet Name Service, WINS. Windows Vista introduced a new implementation of TCP/IP that supports both IPv4 and IPv6 in the same network stack. This new implementation also supports offloading of the network stack onto advanced hardware to achieve very high performance for servers. Windows provides a software firewall that limits the TCP ports that can be used by programs for network communication. Network firewalls are commonly implemented in routers and are a very important security measure. Having a firewall built into the operating system makes a hardware router unnecessary, and it also provides a more integrated management and easier use. Point-to-point tunneling protocol. The point-to-point tunneling protocol, PPTP, is a protocol provided by Windows to communicate between remote access server modules running on Windows Server machines and other client systems that are connected over the Internet. The remote access servers can encrypt data sent over the connection, and they support multi-protocol virtual private networks (VPNs) over the Internet. HTTP protocol. The HTTP protocol is used to put information using the World Wide Web. Windows implements HTTP using a kernel mode driver, so web servers can operate with a low overhead connection to the networking stack. HTTP is a fairly general protocol which Windows makes available as a transport option for implementing RPC. Web Distributed Authoring and Versioning Protocol. Web Distributed Authoring and Versioning (WebDAV) is an HTTP-based protocol for collaborative authoring across a network. Windows builds a WebDAV redirector into the file system. Being built directly into the file system enables WebDAV to work with other file system features such as encryption. Personal files can then be stored securely in a public place. Because WebDAV uses HTTP, which is a get-put protocol, Windows has to cache the files locally so programs can use read and write operations on parts of the files. Named pipes. Named pipes are a connection-oriented messaging mechanism. A process can use name pipes to communicate with other processes on the same machine. Since name pipes are accessed through the file system interface, the security mechanisms used for file objects also apply to named pipes. The SMB protocol supports named pipes, so named pipes can also be used for communication between processes on different systems. The format of pipe names follows the Uniform Naming Convention (UNC). A UNC name looks like a typical remote file name. The format is // server name / share name /x /y /z, where server name identifies a server on the network, share name identifies any resource that is made available to network users, such as directories, files, named pipes, and printers, and /x /y /z is a normal file path name. Remote procedure calls. A remote procedure call, RPC, is a client-server mechanism that enables an application on one machine to make a procedure call to code on another machine. The client calls a local procedure a stub routine that packs its arguments into a message and sends them across the network to a particular server process. The client-side stub routine then blocks. Meanwhile, the server unpacks the message, calls the procedure, packs the return results into a message and sends them back to the client stub. The client stub unblocks, receives the message, unpacks the results of the RPC and returns them to the caller. This packing of arguments is sometimes called marshalling. The client stub code and the descriptors necessary to pack and unpack the arguments for an RPC are compiled from a specification written in the Microsoft Interface Definition language. Programmer Interface. The Win32 API is the fundamental interface to the capabilities of Windows. This section describes 5 main aspects of the Win32 API: access to kernel objects, sharing of objects between processes, process management, inter-process communication, and memory management. Access to kernel objects. The Windows kernel provides many services that application programs can use. Application programs obtain these services by manipulating kernel objects. A process gains access to a kernel object named XXX by calling the createXXX function to open a handle to an instance of XXX. This handle is unique to the process. Depending on which object is being opened, if the create function fails, it may return 0 or it may return a special constant named invalid handle value. A process can close any handle by calling the closeHandle function, and the system may delete the object if the count of handles referencing the object in all processes drops to 0. Sharing objects between processes. Windows provides 3 ways to share objects between processes. The first way is for a child process to inherit a handle to the object. When the parent calls the createXXX function, the parent supplies a securities attribute structure with the bInheritHandle field set to true. This field creates an inheritable handle. Next, the child process is created passing a value of true to the create process function's bInheritHandle argument. Assuming the child process knows which handles are shared, the parent and child can achieve interprocess communication through the shared objects. The child process gets the value of the handle from the first command line argument and then shares the semaphore with the parent process. The second way to share objects is for one process to give the object a name when the object is created and for the second process to open the name. This method has 2 drawbacks. Windows does not provide a way to check whether an object with the chosen name already exists, and the object namespace is global without regard to the object type. For instance, 2 applications may create and share a single object named foo when 2 distinct objects, possibly by different types, were desired. Summary. Microsoft designed Windows to be an extensible, portable operating system, one able to take advantage of new techniques and hardware. Windows supports multiple operating environments and symmetric multiprocessing, including both 32-bit and 64-bit processors and NUMA computers. The use of kernel objects to provide basic services along with support for client-server computing enables Windows to support a wide variety of application environments. Windows provides virtual memory, integrated caching, and preemptive scheduling. It supports elaborate security mechanisms and includes internalization features. Windows runs on a wide variety of computers, so users can choose and upgrade hardware to match their budgets and performance requirements without needing to alter the applications they run. Conclusion. In this chapter, we have covered the following in detail: the Unix system, the Linux system, Windows Server.